On the workbench here, I have a welding and design fail story here. In this video, I'm going to explain what happened and what can be done differently about it. What you're looking at, this metal item here, is the support piece of a plastic bucket seat that you could find in offices or lecture halls or theaters. And the seat bolts down at the four corners to this piece here. This is the underside of it. A stem sticks out from it, and the stem faces down, and the seat swivels in this orientation. Obviously, I cut out the failed part in the middle so we can look at it. So the seat is manufactured originally by Borgo, and the metal piece here from the middle looks like this. It's been the stem that broke off from here starts actually here on this surface and has been welded really solidly all around with a little bit of welding spatter here, not cleaned up, but it's very nicely welded. It's also welded on the inside, you can see like so, double welded for extra strength, but inevitably these all snap off, these stems all snap off in a similar pattern like this one. So let's take a look at what are we looking at. If I zoom in, you can see that the surface of the failed metal here, and all of this is mild steel, looks like this. You can see these striations or hairlines running across, fine hairlines running across the surface to about the middle of the stem. Same symmetrically from the other side, there are these fine hairlines here that meet at this coarse surface in the middle. What you're looking at here is a progressive ductile failure of metal, a form of metal fatigue that starts on the, I don't know, in this orientation, left side and right side together at about the same time, and this progresses in over time in this direction here, and this progresses in this way until there is only this much metal holding in the middle, and then this metal just snaps off in the middle. This is brittle failure in its final stage. So what starts this ductile failure, or what causes this ductile failure here, is the cyclical loading, back and forth loading of this metal piece. Persons sitting down on this chair or rocking it back and forth, however slightly the stem does bend, even if the seat itself is just designed to swivel around like so. People do have a little bit of lean forward, lean back, a little bit of torque is placed on it. And this cyclical loading, you can see how the brittle failure does not line up with the perfectly, it doesn't have to, doesn't line up with the axis of the chair running fore and aft on the chair. It's off on an angle, but it does line up in one other way. This failure was progressing from 4 points. From this corner here where the weld ends and the hole begins, this corner here where the weld ends and the air gap begins, and also from this corner here as well as from that last corner there. So the welds are not placed symmetrically in this direction of rocking. The welds are placed, I don't know, on an angle. That's not a problem. The problem is, and this is why aircrafts don't have a square window, is that the end of the weld here creates a stress riser. It's a stress concentration point. All four corners here, this one as well, this one as well, and you can see it's the brittle failure also goes down there, and ductile failure is also more dramatic in this corner. So most likely failure here started at the let's see, at these two corners here and progressed here as well as so into the middle as well. So if this weld here on the outside, instead of just a weld blob here, if this welding continued to form a continuous circle like this, there wouldn't be a weak point in it. There wouldn't be stress risers, these force stress risers, there wouldn't be any, and there wouldn't be any ductile failure or brittle failure. It would still be bent over time or loaded back and forth, but there wouldn't be this stress riser present, 4 of them, that caused this piece to fail. So that's why the welding is perfect on this one. This is a design failure.